Hi everyone, I'm Anish and welcome to PrepFusion. So today we'll be starting the lecture 7 of the state space equation, right? State space chapter basically. So in the previous two lectures, we learned a bit of mathematics to understand the next few lectures, right? Because the concept of diagonalization is very important. But to get to the concept of diagonalization, I first have to make you understand the concept of eigenvectors, eigenvalues, and to understand eigenvectors and eigenvalues I have to go all the way back. Okay, what is transformation, what is basically matrix, and what is span, okay, what is rank, all those things. I just gave you a basic overview, and this I think you already know in class 11 or 12, but in like semesters also, in engineering also, in semesters you may have studied. So yeah, I just gave you a basic overview so that we can continue with our state space chapter, right? So in this lecture we'll study the solution of state space. What do you mean by solution of state space? So I have the until now what I was doing, I had differential equation, I was plotting it, okay, SFG, and writing the state space equation. Now what I'll do, I will solve the state space equation, right? I will solve it, okay. So there will be multiple cases for this, so we'll go step by step. So first is solution of state space equation, okay. So let me write the state space equations, right? So if I write the state space equation, what are the equations? Remember, what is x dot t equals to? It is equals to a x of t plus b u of t, right? So this was my simply state equation. And what was my output equation? It was y of t equals to c x of t plus d e of t, okay, d u of t. So this is my state equation. This is my output equation. This is my output equation, okay. This is my output equation. So what I will do, I will find the solution for this x dot and y of t, right? This is for the state, like not x dot, basically the state variable. Find the solution of state variable and the output, right? I will take two cases. First case, what I will do, I will make the input 0, okay. If we don't apply any input to the system, then what output I'll get? What output I will get? Due to which variable I will get the output? Due to the state variable, right? State variable may have some initial condition, okay. That's why due to that variable I will get some output also. Like my output will be a combination of both this input and the state variable, right? In the state variable and the input, as you can see from the output equation itself, it is a combination of input and the state variable, right? Like the state variable itself is dependent on the input also, right? Here dependent on the input also. So the main thing is, first what I will do, I will make the input 0, solve for the case 1. So case 1, right? What is case 1? Case 1 is to basically when input is 0, when input is equals to 0, that is u of t is 0. Don't get confused that u of t is unit step. No, u of t is simply the input, like we represent u of t as input here. So when the input is 0, what does it mean? What do we call the output when the input is 0? What response do we call? Just remember, right? We call it 0 input response. So this is 0 input response, okay. This is 0 input response, right? So again I will explain you like a bit of what do you mean by 0 input and 0 state response, so that you can again revise, right? Refresh your mind basically. So the response, right, is of two types. Response is of two types, okay. How? Basically one is the natural response, another is the forced response. So this is the, let's say, let me write this. another is the forced response, right? So what do you mean by natural response? Natural means the response due to which it is coming naturally, right? Natural means basically due to the initial conditions, due to memory based, right? So due to the initial value, and due to the force response, what do we mean by force response? It is due to the output. So this is due to the output. Okay, sorry, not the output. What do you mean? Response is the output due to the input basically. So due to the input. Okay, so this is right. With what initial value, or what you can say, it is memory based input, memory based response. Why? Because the circuit has some memory, right? It has some initial value. Okay, it has some stored memory. That's why we call it memory, because it has some value from the past, right? From the past. So, or we can say memory. This is zero input response, which is a function of initial value. Okay, and this is basically zero state response. Okay, zero state response, as a state is zero in this case, which is a function of input basically. Okay, which is a function of input. So yeah, that was basically a bit of like a revision for you. Okay, what do we mean by zero state and zero input response? I will here take an example also. From there you will understand what do we mean by zero state and zero input response. So let me take an example. Okay, if I take an example, right? If I take an example, so this example, right? Let's say I have one input of 10 volts. Okay, I have some input of 10 volts, and this is some whatever you say, like 1 ohms, and this is some capacitor of 2 farad, right? And I am taking the output from here, VO from here. Now tell me what type of response will be my VO. Will it be zero state response, or will it be zero input response? Okay, will it be natural response or force response? So what is it? What is the response? It is the force response, because I am giving it some input, but my state variable, the voltage, right, it doesn't have any initial condition. Okay, hence it will be zero state response, or we can say the force response, right? Now this is the force response. Okay, now what do we call basically the zero state response? So another example will be zero state only. So now this time you don't have to guess. So this time, right, my input is zero. Okay, but I only have the capacitor, source free network, basically the natural response. This is 2 farad, and this is again 1 ohm, let's say. And this time, right, I have some initial condition to the capacitor. What is the initial condition? So initial condition, right, initial condition is simply let's say it's 5 volts only, 5 volts only. This time, right, if I measure the output voltage, what will be that, like, response called? It will be called the natural response. Okay, so this is a basic point that we need to understand. So let's come back to our solution, right? We have to solve for the state transition equation when the input is zero. So if the input is zero, right, what will my equations become? What will my state equation and output equation become? So they will become, right, simply B and C will be zero, right? Not B and C. B and C will be eliminated. We have to only find A and C. Okay, we have to only find A and C. Sorry, we have to, like, only A and C matrix will come into the equation, right? So x dot of t equals to simply A x of t, y of t equals to C x of t. Okay, so this is my equation that it becomes. Now let me write the state transition equation in time domain, right? Basically in time domain, in differentiation format. So state transition equation in basically the differentiation format. So it is dxt dt equals to a times x of t, right? This is, let me change the color, this is in differentiation format, right? So this is basically the equation. Now what is my output equation? Like output equation is this only, okay. Y of t equals to c x of t, okay. Now right now, like this is, what is this response called? This is called the natural response, right? As the input is 0, okay, as the input is 0. So what we can do, we can simply solve using Laplace, okay. We can simply solve using Laplace. Why? Because the system is linear, right? Our system is linear, okay. That's why we can simply solve for with the help of Laplace, okay. We can take the Laplace transform, right? We can take the Laplace transform. So wait, if I take the Laplace transform of this state equation, right? If I take the Laplace transform of this state equation, what will I get? I will get simply s x of s minus x of 0 equals to a times x of s, right? So this a is just a constant matrix, right? So this a can come out, and other things I converted into Laplace domain, okay. Now why this x of 0 came, like I've already explained you, still I will explain it once more to you. This x of 0 won't come in one of the cases. For if few people who have already learned Laplace, they will understand, right? So basically, right, one is unilateral Laplace, another is bilateral Laplace. Okay. So for unilateral Laplace, right, we define the Laplace transform like if our signal only exists after t equals to 0, we only take the unilateral Laplace, okay. And most general cases we take the unilateral Laplace only. So the transform, right, Laplace transform, it becomes like this. What does the Laplace transform become? It becomes 0 to infinity, okay, 0 to infinity f of t e raised to power minus st dt, right, dt. Now this is for causal signals. So for causal signals, our Laplace transform, what does it become? Basically, if I take the differentiation, right, if I take the differentiation of f of t, the Laplace transform of this one, right, will be simply s times f of s minus f of 0, right, minus f of 0, okay. Now if I take the like the Laplace transform of bilateral, right, so what does the definition say to us, right? So definition, right, f of s, let's say this is f of su and this is b, bilateral and unilateral. So this is going from minus infinity to infinity, okay. This is going from minus infinity to infinity, f of t e raised to power minus st dt, okay, f of t e raised to power minus st dt. So right, so what will be my Laplace transform of the differentiation this time become? So it will be, right, df of t dt, the Laplace transform of this, okay, Laplace transform of this will simply become s f of s, okay. There won't be any term coming x of 0, right, x of 0. So yeah, that is the difference between this one and this one, okay. Let me like reduce the size of this a bit, okay. So yeah, this is basically the difference between unilateral and bilateral Laplace, okay. Now right, now let me solve this in the Laplace domain, this equation, right, this equation in Laplace domain. So what does my state equation become? So this, right, again let me copy this. So what I can do, I can take the like x of s in this side and x of 0 at this end, right. So s x of s minus of a x of s into x of 0. And what do? I take x of s as common, right? So I hope you understand that this is s and these are in like matrix format, right? These are in matrix format. That's why I have to multiply a I with this. Like I in normal simple absolute format is 1 only. Okay, so if it is a 1 cross 1 matrix, now if it is a 2 cross 1 matrix, it is identity 1 only, but it's according to matrix 1, right? So that's why I have to multiply I, because I'm doing operation with another matrix, right? A. Okay, that's why this s, right, is becomes si. Okay, so I hope like that like you understand that. Okay, because x is also in matrix format. Now minus a, this becomes x of 0. Okay, now what do I need to do? So I need to post multiply. I need to, whatever you want to do, if what you can do is post multiply or pre multiply. So one mistake I have to like in general cases, right, in general format, what do you do? We write this in front of x of s instead of back of x of s. That's just a general convention, it doesn't matter. Okay, so what I will do is okay, the mistake that I made is this x of s, right, is in like post multiplication. So I have to take x of s common in the post only, right, in the post only. Okay, that was my mistake. Okay, that was my mistake. So yeah, that's why like this x of s is taken common up here. Okay, because this is post multiplied with s and this is post multiplied with a as matrix multiplication, right? We can't simply, it doesn't follow the commutative law. Okay, x of s into a, we can't take common here, right? We can't take common x of s just because these two are post multiplied. That's why we can take common here. Okay, so I hope that also clears your doubt. Okay, just I made the mistake. Okay, mistake can happen with me also. So yeah, now what I will do, I will take the pre-multiplication of the inverse of this, right? So pre-multiplication of this one. So okay, let me write this. This minus 1 equals to si minus a inverse into x of 0. Okay, so this like any matrix, right, multiplied with this inverse becomes identity only. So it becomes x of s only. It becomes x of s only equals to si minus a inverse x of 0. Now what does this like x of s become, right? What does this x of s become? So this x of s, right, if I take the inverse Laplace of this, taking the inverse Laplace, right, taking the inverse Laplace, what do you get? I get x of t equals to Laplace inverse. This x of 0, right, is a constant, so this x of 0 can go outside the Laplace inverse of simply si minus a inverse, and this is x of 0, right? This is simply x of 0. Okay, this is simply x of 0. Okay, so yeah, what will be the Laplace inverse of this? So like this will be a bit confusing to you, but the Laplace inverse of this, right, the Laplace inverse of this will be e raised to power at. Okay, the Laplace inverse of this x of t will become e raised to power at into x of 0. Why? Like you can relate it like this one, that if I like do this in normal number format, right, non-matrix 1 cross 1 matrix, okay, single elements, this si minus a inverse becomes s minus a. And what is the Laplace transform of, like Laplace inverse of s minus a or s plus a? It is e raised to power minus at. For s minus a, it will be e raised to power plus at. So Laplace inverse of s minus a is e raised to power plus at. Okay, e raised to power plus at. So yeah, from there you can relate that how does this come, right? How does this come up? Okay, so yeah, this, right, this matrix is also known as state transition matrix. Okay, e raised to power at, this matrix is also known as state transition matrix. So this we can call as state transition. So let me, like, how is it written in symbol? It is written as phi of t, as it tells the state or like state transition of the state variable, right? So basically x of 0 is some value and multiply with the state transition matrix, I can get the value of x of t, the state variable, at any time t, right? That's why this is called the state transition matrix. At any transition, I can set the value, I can see the value of the state variable. Okay, so this is known as state transition matrix. Okay, so phi of t equals to e raised to power 80. Okay, 5 equals to e raised to power 80. So yeah, that's what we learned until now. That's basically we made the input 0, right? We made the input 0. Okay, we made the input 0, and I have to find the response for like 0 input response, right? So I have to find the value of state variable and output value, right? So A and C are given. So in terms of A, I found out the state variable basically here, right? Found out the state variable in terms of A, right? This one. Okay, so this is very, very important. So this you have to remember. This you have to remember, and this one also. Okay, because most of the times what we'll do, we'll not find this e raised to power 80. We'll find this inverse and then take the Laplace inverse. Okay, then take the Laplace inverse instead of finding this e raised to power 80 and then solving, right? It will be difficult. We'll find this si minus a inverse in Laplace domain only and then solve, or we can solve like this. This is one method and this is another method. Okay, so yeah, that is the main point until now. So let's now solve a question, and from there we'll understand better, right? From there we'll understand better, like how do we solve these questions, right? So we have been given for the given state equation, and also the initial condition are given, right? Initial condition of the state variable are given. What we have to find? We have to find the state variable themselves at t equals to 2. Okay, at t equals to 2, we have to find the state variables, right? So how do we do that? So basically, right, what we will do, I will solve this using two methods, one in the time domain, another in the Laplace domain. So this is the matrix. So see this and try to write in your notebook, solve it by yourself. Okay, then you see my solution. Okay, so first, what will be my first method? It will be time domain analysis. It will be time domain analysis. Okay, so for time domain analysis, right, what do we know? We know my state variable x of t equals to e raised to power 80 times x of 0. Okay, e raised to power 80 times time 0. Now you might ask, how will I find this e raised to power 80? Here, right, the concept of diagonalization will help us. Okay, the concept of e raised to power 80 equals to what? Diagonalization. I forgot the spelling, so excuse my spelling actually. Okay, I think I made a mistake here. Okay, now it's correct. Sometimes this happens. Okay, so yeah, how do I find the e raised to power 80, right? So in normal without matrix, right, what is e raised to power 80 equals to? Expansion form, right? Series form. What is it? So it is basically e raised to power 80 equals to 1 plus 80 by 1 factorial. Okay, then 80 square by 2 factorial, and this goes on till infinity, right? This goes on till infinity. Okay, now here, right, this is like, let's say this is in matrix format only. Now I just wrote the single like element format. Now this is, let's say this is in matrix format, right? So this I can expand like this. This is nothing wrong, right? And A is the matrix, right? A is the matrix. Okay, that's why you understand that this e raised to power 80 is just not simple, right? We make the elements, each elements raise it to the power of exponential, right? I mean exponential raised to the power of the element, right? So we don't simply, we can't simply do that. Okay, this is some operation. Okay, this is some operation, just like I multiply 2 with the matrix, so every element gets multiplied by 2. So if I do exponential of that matrix, it's not like that every element will be exponential. All right, exponential, no, it's not like that. Okay, it's not like that every element will be exponential. Okay, no, yes, every element will be exponential, but it will not be simply like this element exponential of that element and this element, right? No, we have to apply this, break this down into simple quadratic form, so that I can do multiplication operations with the matrix. Then only this e raised to power 80, right, I can find in matrix format. Okay, this I can do, right? This I can do simple multiplications formats, right? So now what is my a equals to? So here, right, concept of diagonalization will come. There I wrote a, like if I diagonalize this, so in diagonalized format, what will be my a equals to? It will be v d diagonal matrix times v inverse, right? V d v inverse. So here instead of writing v, I am writing m d m inverse. Okay, m inverse, don't worry. Okay, don't worry, just a nomenclature. Vector was for that only, that's why I'm not writing vector here. Okay, so this d, right, d is diagonal matrix. Just from the previous lecture we have studied all this, right? So this shouldn't be that big of issue. Okay, d is diagonal matrix. So now, right, what I can write the e raised to power 80 as? So e raised to power 80, right, e raised to power 80 is simply equals to m times m inverse. Okay, m times m inverse plus a times t, right, a times t. So t will be outside only, but what I can write a as like this, right? I can break down the a as like this. So it will become m d inverse times t only. Again this, right, the what will be my second element become? So my second element will become simply m times d square m inverse. Why? This has, we have already covered this in the previous lecture, right? If we multiply like the two if I take the power of a matrix, right, only the diagonal matrix will be raised to that power and the eigenvectors will remain same, right? So I hope like you're revising the previous lectures, right? So this becomes, the eigenvectors remain same. This, right, this is raised to the power 2 and this is m inverse divided by 2 factorial times t, right, divided by 2 factorial times t. Okay, so this is m inverse divided by 2 factorial times t. So yeah, this is my like expansion of the series, right? Now what I will do, again, I can take common, but don't just take common blindly, right? I can take m common because it is multiplied in pre with all of the matrices. So m I can take common. Okay, m I can take common in the pre, right? M I can take common in the pre. Now this is an m inverse, right? M inverse I can take common in the post, because t is just, this t is just a like scalar value. Okay, t is just a scalar value, so that is not an issue. So m inverse I can take common for the post and m I can take common for the pre. So this becomes I only. Okay, plus this becomes d times t, plus this becomes d square. Oh, so this also becomes t square. Sorry, I forgot this also becomes t square. So this is 2 factorial plus dot dot, right, plus dot dot. Okay, so yeah, and in the post I have a m inverse, right, m inverse. Now what is this series looking something familiar to? Is this series looking something familiar to? So here, right, I should also write this not as 1. This also I should write here is I also, because this is in matrix format. Okay, previously it was in element format, that's why I didn't wrote I. Okay, I, like, just in matrix format, if you want to replace one, right, just replace it with I wherever possible. So yeah, I just follows the property of 1 only in normal element format. So this series and this series are similar only, right? So what will this become? This will become e raised to power dt m inverse. Okay, so this is what my e raised to power 80 is equals to. Now you might ask, like, it was like same only, right? It is same only, right? Because like I was finding e raised to power 80, but now I have to find e raised to power dt also, but now I have to find the eigenvectors also. So what is the difference here? Why is it so easy? So why is it easy? Because one thing you have to note is that if I do d square, right, if I do d square, what do I get? I get the like the eigenvalues of the diagonal elements are powered by that same. Okay, let me expand this. By there you will understand, right? So let me say, for example, okay, for example, I have a 2 cross 2 matrix, right? 2 cross 2 matrix, n equals to 2, right? Or like order is 2 cross 2. So what will this expand to? So this is M. Okay, now this is I only. Okay, let me write the whole matrix format itself. From there you will understand. Okay, this is like, okay, this is 1 0 0 1. Okay, everything will be in 2 cross 2 format. Now this is right, this will be D only. So what is D? Lambda 1 0, this is 0 only, and this is lambda 2, and this is times D. Okay, now plus, this is the more interesting part. Okay, this is T, you will not understand, this is T. So now the more interesting part, this is lambda 1 square 0, lambda 2 square. Okay, this is T square, right? So if I square a diagonal matrix, only the diagonal elements get square, right? Other elements remain 0. So this is the simple property. That's what we'll make use of. So here's the inverse. So now, right, I can again expand this. Okay, in single matrix, right? I can again expand this in single matrix. So again, right, this is 1 plus lambda 1 T, because T is getting multiplied over here, right? Plus lambda 1 whole square T square. Oh sorry, I have also a 2 factorial over here, right? 2 factorial over in this end, right? So by 2 factorial, and it is going on like this only, right? Now this end is 0 only. Every element at this like second column, right, of the first row is 0 only. Now the first column or the second row is also 0, but the final element, right, second column of the second row is getting added up like this. Okay, so this is also 1 plus lambda 2 plus lambda 2 square. This is T also. So T square by 2 factorial plus okay. So yeah, this is what my like becomes like the matrix becomes, right? Matrix becomes, okay. M inverse. So yeah, now I hope you again recognize this series, right? Now this is scalar, right? This is scalar. You can easily recognize the series. This is e raised to power lambda 1 T, and this is e raised to power lambda 2 T. Okay. So yeah, now I hope you are understanding. This becomes e raised to power dt only. Why? Because simply we just raise it to the power, so that's why I write it e raised to power dt only. Okay, that's why I write it e raised to power dt. Okay, so actually I should write this after this proof, actually, like here, and that would be more like in sequential manner. So let me say this is here only, and this is m inverse. Now this e raised to power dt, right? I can simply expand this. Okay, so this becomes m, like for a 2 cross 2 matrix, right? Simply e raised to power lambda 1 T 0 0 e raised to power lambda 2 T. Okay, so yeah, this was the basic crux, right? This was the basic crux of this proof. Okay, so yeah, I hope you got the proof. Now let's solve the question, right? The question was important, so let's go for the question. So what is the question asking us to do is, so lambda 1 lambda 2, what is this for this question, right? Lambda 1 lambda 2. So let me take the matrix again. So matrix is the same matrix as we are using 100 times now. Okay, what is lambda 1 and lambda 2 for this case? Tell me. So lambda 1 lambda 2, right, for this case is simply lambda 1 equals to simply 2 and lambda 2 equals to simply 3, right? Okay, it's simply 2 and 3. Why? You can check from the trace. So the trace, if the addition of the diagonal elements is the addition of the eigenvalues, also the the determinant of the diagonal element, determinant of the matrix is the multiplication of the eigenvalues. Okay, so yeah, both of them are matching. So now, right, right? Now what we'll do is what are the eigenvectors corresponding to these eigenvalues. So I hope you remember, like this has stuck in your mind for now. The same example that I'm taking is like eigenvector corresponding to this, I think I took as 1 minus 1, and eigenvector corresponding to this I took as, I think, 0 and 1, right? 0 and 1. Okay, so my what will be my m or the v vector, right? That was the column matrix of the each eigenvector, right? Each eigenvector. So my m, right, m matrix will be something like this. It is 1 minus 1, 0 and 1. Zero and 1. Good. It is 1 minus 1, 0 and 1. Okay. So now, right, now what will be what will be the equation? So I will put this in the equation. So we have to find the the quotient, right? So for quotient, for finding the x of t, we have to find the e raised to power at, and we went to this direction, right, to find e raised to power at. So x of 0 we know, but we have to now compute the e raised to power at. So for computing e raised to power at, what will compute? Simple m d m inverse, right? So m, what we have is 1 minus 1, 0 and 1. Okay, 1 minus 1, 0 and 1. And what is e raised to power 80? E raised to power 80, right, is just e raised to power of this eigenvalues, right? E raised to power of this eigenvalues, not 80, sorry, e raised to power dt, right? E raised to power dt is just e raised to power of the eigenvalues, right, on the diagonal elements. So e raised to power 2t, this is 0, 0, and this is e raised to power 3t. Okay, and this is 1, 0, 1. So yeah, this is basically the matrix. So yeah, now I will just simply do the multiplication and solve it. So this is, right, 1 times e raised to power 2t, 0 times 0, so this is e raised to power 2t itself, and this is 1 times 0, 0 times 0, so this is 0 itself. This is minus 1 times e raised to power 2t, 1 times 0, so minus e raised to power 2t, and this is minus 1 times 0, and this is 1 times e raised to power 2t, 3t, this is e raised to power 3t. Okay, e raised to power 3t. And what is this? This is 1, 0 minus 1, 1, right? 1, 0 minus 1, 1. So what does this become? So this is, right, this is e raised to power 2t times 1 and 0, right? So this becomes e raised to power 2t itself, and this is minus e raised to power 2t. Okay, this is 0, right? 0 times, okay, sorry, the next element, this is e raised to power 2t times 0 and 0 times 1, so this is 0 only, and this is minus e raised to power 2t plus again this is also okay, sorry, I made one very big mistake. What mistake did I make? Just tell me. I know you are screaming that I have to take the inverse of this also. So for taking the inverse, right, this will become plus, and what will happen? The determinant, right, is 1 only in this case. So this determinant will be 1 only. So I won't write. So yeah, up until now everything was correct. So this is e raised to power 2t times 1. This is 0. So this is correct. This is 0, 0, and this is correct. Now this, right, this is minus e raised to power 2t times 1, and this is plus e raised to power 3t. So this becomes minus e raised to power 2t plus e raised to power 3t, and this becomes what is the last element? This is 0, and this is e raised to power 3t. So last element, right, is e raised to power 3t. Okay, so yeah, this is my final element, basically, like final e raised to power 80, right? E raised to power 80. So now, right, now what will be my x of t equals to? It will be e raised to power 80 times x of 0. So x of t equals to, what is e raised to power 80? It is simply this matrix, right? Let me copy this. This is x of 0. X of 0 is simply, what was my x of 0? It was minus 1 and 1, right? x1, x2, so it is minus 1 and 1. Okay, So minus 1 and 1. Okay, so I have you noted down the question, and so like you are checking where your step or mistakes you made. Okay, so it is very important to solve by yourself. If you don't solve questions by yourself, then it will be very difficult to crack the gate exam, right? Crack the gate exam. So now what will my xt become? It is simply e raised to power 2t times this one minus 1 and 0, right? So minus e raised to power 2t. Okay, now this is minus e raised to power like this one, and plus e raised to power 3t plus this. So only we are remained with e raised to power 2t only. Okay, e raised to power 2t only. So now, right, what is the question asking us to find is we have to find a value of x of t, the state variable at t equals to 2 seconds. So put t equals to 2 in the column matrix. So we get e raised to power minus 2 and e raised to power 2. Solve for it, like you find the like exact values, and you will get your answer, right? So now, right, I will do in the second domain, like second method. Frequency domain analysis, right? So in frequency domain analysis, what I will do, simply, right, what I had is x of t equals to e raised to power 80 times x of 0, but I had another format also. What this, right, x of t equals to Laplace inverse of si minus a inverse, right? Si minus a inverse into x of 0, si minus a inverse into x of 0. Okay, so this is basically the what my x of t is equals to. So I can solve this in this format also. I will solve the si minus a inverse, then I will find the Laplace inverse, then I will do the time domain like multiplication, right? So what is si minus a inverse? So like first let me find what is si minus a. So si minus a, right, is this one, right? S0 0 s. So s times I, you will get this only. So s is simply a scalar, okay, but like I is a matrix, that's why you get it like this. Now what is a matrix? So I think you have already mugged it up for now. A matrix is 2 0 1 3. So 2 0 1 3 2 0 1 3. So like what will it be equals to? It is s minus 2 0 minus 1 and s minus 3. Okay, s minus 2. So this is my si minus a, right? Si minus a. Now what will be my like, okay, I'm out of pages, let me take few more pages. What will be my si minus inverse, si minus a inverse? So simply write si minus it is simply s minus 3, s minus 2 and 0 1. Again I have to divide by the determinant also, right? So swapping the diagonal elements and making the signs opposite of the diagonal elements. So what do I get? So yeah, this is what basically the inverse is, right? So now, right, expanding this is simply s minus 2, this is 0 only, this is 1 by this s minus 3 times s minus 2. Okay, this is 1 by s minus 3. Okay, now, right, now what will be my like time domain expression? So what I have to do is simply take the Laplace inverse of this, right? Laplace inverse of each elements. Okay, that is not an issue. I can take the Laplace inverse of each elements. So the Laplace inverse of each element of this, right, this matrix will become phi of t. So Laplace inverse of this one will become e raised to power 2t. Okay, this is 0 only. Now this one you do partial fraction. So you put s equals to 3. What do you get? S equals to 3. If you put, you get e raised to power 3t. Okay, because the coefficient, like here I put 3, so 3 minus 2 is 1, so 1 by 1 into e raised to 1 by s minus 3, so this is e raised to power 3t. Now I put s equals to 2, so this is 2 minus 3 minus 1, so minus e raised to power 2t. Okay, so this is simply equals to 0. Okay, this is 0 and this is simply e raised to power 3t. And this is u of t multiplied, as this is a unilateral signal. Okay, this is a unilateral signal. So again, right, for finding x of t, what I will do? For finding x of t, I will simply just multiply the matrix, right? Multiply the matrix. Okay, the quotient numbering, right? I have to remember the quotient numbering also. I will change the quotient numbering. Okay, no worries. So okay, this x of t, right? This x of t, what will it be? It will be simply this matrix, right? Multiplied with x of 0. Let me remove the this is x of 0. What is x of 0? X of 0 is, from what I remember, it was minus 1 1. Yeah, minus 1 1, minus 1 1. Okay, so this becomes, right, this becomes e raised to power minus 2t. Okay, and this becomes the denominator becomes e raised to power, this 3t cancels out. Okay, minus and plus cancel out, only we remained with e raised to power 2t again. So I am getting the same expression as previous case, right? So x of 2, right, x of 2 will be again minus e raised to power 4. Okay, did I do like, I did something wrong? Okay, okay, this was, yeah, this should be 4, right? This should be 4. This t was 2 seconds, so yeah, this should be 4, so that's my apologies. Okay, so yeah, this should be 4 and this should be 4 also. Okay, so yeah, as this is not live class, right, so you guys can't scream at me, yeah, sir, you have made a mistake, okay, but I will rectify it by myself if I identify it. Okay, so yeah, this is e raised to power 4 and this is also e raised to power 4. Okay, so these things you have to like very like what do you say, identify about, right, in a gate exam itself, because yeah, these silly mistakes will occur generally. So generally, like I put t equals to 1, so I was thinking in my head I put t equals to 1 and this came. So this is how you have to like understand that you can't make mistakes like this. Okay, so it can happen with me also, because yeah, this did happen during my preparation, but I practiced so much so that this like I won't make this mistake. My brain will be automatically like coded to not make this mistake, right? Hard coded basically. So yeah, these things you have to be careful with. So yeah, this was x of 2. Now let's solve for another question. This is the next question. So in this question, right, it has told us like this was two methods, right? So it has again given us a state equation. Okay, a raised to power 20. So a, right, a in this case is this matrix only 2 0 1 3, and again like initial condition same only, and again we have to find the value of x1 and x2 at t equals to 2, basically the state variable at t equals to 2. But what is different here? The difference is the matrix, right, that is here, it is not simply a, it is a raised to power 20. So right, if you try to do this with in Laplace, it will be very difficult. Why? Because you have to find the Laplace inverse of si minus a raised to power 20. Now how will you find a raised to power 20? That is difficult, right? That is difficult. But what you can do is either a raised to power 20, you apply the diagonalization method, and from there what you can do is a raised to power 20. So a raised to power 20, right, a raised to power 20 will be equals to simply m d raised to power 20 m inverse. Okay, so d raised to power 20 is very easy to find. How? So it is simply m, if it is 2 cross 1 matrix, so basically in our case, right, so it is 2 to the power, okay, sorry, what are the eigenvalues? It is 2 and 3, right? So this is 2 to the power 20, and this is 0, and this is 0, and this is 3 to the power 20, right? And what were my eigen values basically? Okay, let me check it from the previous question basically. So it was, I think, where is it? Yeah, this one, right? 1 minus 1 0 1. and what is this? So this is right, this is 0 1 1 1. Okay, the inverse basically. So like you can solve it, you can solve it again. So what would you get? I will write 2 to the power 20 as like lambda 1 dash, and this 3 to the power 20, right, as lambda 2 dash. I hope you are understanding how I am raising this direct to the power 20, right? So all this I have explained it multiple times. So this, right, this becomes simply 1 into lambda 1 0. So this becomes lambda 1 dash, and this is 0, and this is 0, this is 0 only, and this is like minus lambda 1 dash plus 0 only. Okay, I need to move this. Okay, not 0, this is lambda 1 dash plus lambda 2 dash. Okay, lambda 1 dash plus no, this is only minus lambda 1 dash, sorry, I don't know. And this is basically what, this is lambda 2 dash, right? Okay, this is lambda 1 dash 0, so this is simply equals to lambda 1 dash, and this is what, this is 0, this is lambda 1 dash, and this is 0, so again this becomes 0 only. Okay, and this is minus lambda 1 dash, and this is lambda 2 dash, so this is minus lambda 1 dash plus lambda 2 dash, so this is plus only. Okay, and this is simply 1. Okay, this I have already solved, right? This is not 1. Okay, this is lambda 2 dash, right? Okay, so yeah, now what you will do, you will do si minus a inverse. You will do si minus a inverse, si minus a inverse. Okay, then what you will do, you will find the Laplace inverse of this. Okay, there you will find phi of t. Now for x of t at t equals to 2, what you will do, you will do phi of 2 times x of 0, right? So this you can do, this is one method, right? This is one method. Okay, so this is like, you can do this obviously, like it's your wish, right? So but what I prefer is the second method. What is the second method? So the second method, right, is this one. So method 2. Okay, so again the time domain analysis basically. So what is x of t equals to? X of t equals to simply e raised to power at, which is the state transition matrix. Okay, this time, right, I will write it this as a dash t, because a is changed into x of 0, right? Now what is my e raised to power a dash t? So it becomes e raised to power, this is a matrix which has been raised by power 20 times t into x of 0. Okay, into x of 0. So this is simply e raised to power at equals to, now what is my e raised to power at equals to? Again, right, what I can write, like I've already proved this one, it is e raised to power dt m inverse, right? E raised to power dt m inverse. Okay, so what is my e raised to power a square of t? So it is simply e raised to power, like I will make it just d square of t, right? D square of t. Okay, d square of t. So I hope you are understanding now the analogy, right? It is simple on. So a for a square it becomes d square, right? Only that change, eigenvectors remain same. So yeah, this is the important point to note here, right? This is the important point to note here. Okay, so like what you could have done is first written like that one only. So like a square will be equals to m inverse d square only. So this is what our value changes for e raised to power 20t. What will happen? The eigenvectors will remain same, the diagonal matrix will change. Okay, you can just prove it, right? You can just prove it. Okay, so only d will change. Okay, so yeah, this is what will happen. So what are my lambda 1, lambda 2? So basically, right, my lambda 1, lambda 2, again like the same thing only, this one only. So d raised to power 20, what will it become? It will become this one only, right? This one only, right? It will become this one only. So what I will do is I will just copy this and paste this over here. Okay, this is my e raised to power, okay, this is my d raised to power 20t. I haven't multiplied t8, t is in the outside, so this is my d raised to power 20 simply. So right now, what is my e a raised to power 20t? So I will assume this as simply lambda 1 dash and this as lambda 2 dash. Okay, so what will be my e raised to power 20t? So my eigenvectors again will remain same. This is 1 0, this is e raised to power 20 t here, right? So this I will write here is e raised to power lambda 1 t dash 0 0 e raised to power lambda 2 t dash, and this is what, this is the inverse, right? So this is 1 1 0 1. Okay, so now you simply again solve this, right? You simply again solve this. What do you get again, right? Like now it is getting repeated, so I will write the expression finally here, like what is coming here, only the one with negative sign, this one is coming, right? This one is coming. So the first one is first element only, so it is e raised to power lambda 1 dash t, this is 0 only, and this is minus e raised to power lambda 1 dash t plus e raised to power lambda 2 dash t. Okay, and this, right, this is lambda 2 dash t only. Okay, so this is my final matrix. Now again, what will be my answer? So for getting the answer, right, for getting the answer, what I will do is simply okay, let me x of t, again this is phi of t only, phi of t only. Okay, so phi of t at t equals to 2 times x of 0. Okay, what is your homework? Your homework is, you don't have to do it for power 20, do it for power 3 and check whether this method is working, like this method is matching with the answer of the previous method, right? These two methods, right? Just check, right, if both of these methods are working. Okay, this is your homework. So few tasks you should do also yourself. Check for power 3, right? Check for power 3 for any other matrix. Okay, for any other matrix which has negative eigenvalues. Okay, this is your homework. So yeah, that is it for this question. So basically what we did, we found the solution of the state equation in this lecture, basically for zero input response, right, when it is a natural response of the system. So how to find it? So basically we make u of t 0, we are left with only these two equations. Okay, still I haven't found the output response. It will be simply just c times x of t, right? C times x of t. If I have given the c matrix, then I can simply find this like output response, right? Response of the output. So for now the question hasn't asked us. In the next few lectures it will ask us. Okay, so yeah, this was basically now natural response. So I told you the difference between unilateral and bilateral. Unilateral means for causal signals for t greater than 0, and bilateral means it exists before like t equals to 0 and after t equals to 0 also. So yeah, the Laplace of the differentiation is a bit different for both of these types of signals, right? So yeah, then we like equated and we got two equations, one the time domain equation and one the Laplace domain equation. So most cases we'll solve the Laplace domain equation. Okay, but sometimes it is easier for us to solve the like time domain equation, right? Time domain equation. Okay, so yeah, so why is this becoming a raised to power 20, right? So I've already proven it to you, right? So where did I prove you? Okay, where did he go? Okay, in the first question, right? First question, I've already proven it to you, this, right? So this becomes this one only, and e raised to power 80 becomes e raised to power d20. Now if I had make this e raised to power 20, right? So this everything becomes raised to power 20, and just the outside 20 remains and everything else remains same. So that's why I will get the same matrix again. So the homework is to also prove for that. Okay, homework is also to prove for that. Okay, so yeah, that is what we did. I proved how I got this equation, right? How I got this equation, very important. Proof is like not important for gate or all those things, but conceptually to understand all these things, right? Very important. So yeah, then I solved one question. Okay, found the value, made a mistake, silly mistake. Okay, then I solved the second question. This is a frequency domain analysis. This is, you might say, is much faster. Okay, much faster, will much faster find phi of t. Most cases you will use this only, okay. But when you are not able to find the Laplace inverse, or like si minus a, you're not able to find, then you have to go for the time domain method, right? So time domain method, where this something power comes up, then you can use the time domain method. So yeah, you find the power of this. Like this is the first method. This is bit difficult, right? Because these are powers. Now what you do, you have to subtract si minus this one, and then take the Laplace inverse, which is same only. Okay, you can do that. Okay, whichever you feel is comfortable. I told you both of the methods. Now this method is the more elegant method, right? So you just change this, the eigenvectors will remain same. You have to prove it. Why? Okay, and then I solve the equations. Okay, find the state transition matrix, and then you find the value. Okay, this was just a dummy question, that's why I didn't find the answer. So yeah, what is the important thing, what we will do in the next lecture is write the properties of the state transition matrix and solve few more questions. So yeah, that was it basically for this lecture. Yeah, I will see you in the next lecture.